Hello teachers, welcome back to section 3-4. We're talking about multiplication and specifically multiplication algorithms in part 2 of this video. So what do we have going on here? Well, we're trying to show an algorithm to multiply. What are we actually multiplying? It's hard to see on this page, but it's 13 times 3. The ultimate goal is just to multiply 13 times 3. It's way over here in the far corner, right here. Okay, now how could we do that? Okay, well, a couple of ways. We could break up the 13 as, notice here, one set of 10s and 3 1s, and we're multiplying that by 3 1s. So you'll see depicted above is the one set of 10 and then 3 1s, and the 3 over here is the times 3 that we've got going on. Now a good way to do that is to split up the 13 as 10 plus 3. Remember, that's expanded form, 1 10 plus 3 1s, or 10 plus 3. And then when you multiply by 3, you're multiplying each of those by 3. So 10 times 3 gives us 30, and then 3 times 3 gives us 9, and we combine those together to get 39. You could also do that vertically, right? So you say 3 times 3 is 9, that's the ones place. 3 times 10 is 30. Or, like we typically do, 3 times 3 is 9, and 3 times 1 is 3. So these are all different models to show multiplication. What about a trick for multiplying by 10 to some power? Well, to multiply by 10, let's think about what this means as far as base 10 blocks go. You would replace each piece with a base 10 piece. So each unit piece, the little squares, with a base 10 that represents the next higher power of 10. Replace each unit with a long, and replace each long with a flat. We've got a picture here. Okay, so you would replace a long, remember this thing right here, I'm highlighting, that's called a long, and you replace that with a flat when you multiply by 10. So 23 times 10, that's what we're actually calculating here, 23 times 10. And so, again, this long is replaced with a flat. This long is also replaced with a flat. The unit is replaced with a long, all 3 of them. And that shows that 23 times 10 is 230. You know, the quick thing to do is just do 23 times this and then whoop, throw down the 0. But the thing is, why? Why is that allowed to do? You never want to do anything unless you can fully explain why. And these base 10 blocks do a wonderful job of fully explaining what's going on. Now this expanded addition, this is really one of my favorite methods. So 4 times 367. All right, so again, the standard algorithm is we just take 367 times 4. And of course, we remember 4 times 7 is 8. And then we put the 2 up here in the tens place because we're regrouping. We used to call that carrying, we're regrouping. And then 4 times 6 is 24. Plus we have those twos, which are really tens, that we regrouped, and that's 26. So I bring down the 6, carry the 2, and so we're regrouping now 200. We have 200s up here. 4 times 3 is 12, plus 2 more is 14. That's just the standard algorithm, but let's look at this in more detail. What if I write 367 expanded? Okay, what does that mean? So it's 3 times 10 squared, because that's in the 10 squared position, plus 6 times 10, plus 7 times 1. Remember, we've been doing that quite a bit when you have something other than base 10, say a base 2 or a base 5 number. That's a good method. Now we're going to multiply that by 4. To do that, we could use the distributive property, right? So I am calculating 4 times 3 10 squared plus 4 times 6 times 10 plus 4 times 7. So the 4 goes in front of each term. Again, that's the distributive property. So we're going to distribute multiplication over addition. Now you know what I'm going to do? I'm going to regroup, okay, or use the associative property. It's different than the carrying regroup, so I need to be careful here. It's an associative property. Look, we put the 4 and the 3 together. So originally it's 3 times 10 squared, but now I'm doing the 4 times the 3 and regrouping. I'm going to do the 4 times the 6 and regroup, and the 4 times the 7 stays. What next? How about let's actually multiply. We know 4 times 3 is 12, and 12 times 10 squared gives us 1,200. 4 times 6 is 24, times 10, like we just talked about it a minute ago, is 240, and then 4 times 7 is 28, and of course you can add all those together to get 1,468. Is that what I got before doing the standard algorithm? It is, but this really does a good job of explaining why that's the case. You have 4 300s, you have 4 60s, and you have 4 7s, and we just add all that together. And essentially, this is just a vertical way of handling that over here to the right. It's the same idea. If you'll notice 4 times 7, that's the first row is 28. 4 times 60, because that's what you're really doing. You're not doing 4 times 6, you're doing 4 times 60 is 240, and then 4 times 300 is 1,200, and add down. Now in the next number, we're attempting to multiply 23 times 14, and we're using our base 10 blocks. Okay, so 23 times 14. Notice what's happened here. The 23 we broke down into 20. Okay, so highlighted here, I'm going to highlight with something bright like pink. So here is my 20, which is going to take 2 longs, right? My 20, and then my 3. So there's 23. Why am I doing 10 of them? Because we're breaking 14 down into 10 and 4. 23 we're breaking down into 20 and 3. And then we do the multiplication, and you see what happens. So we have the 20 times the 10, which gives us really 2 flats. And then the 3 times the 10 is going to give us 30 over here. And down here, by the way, the 2 flats is the 200 listed at the top of the screen. And then the 4 from the 14, you have longs. Say 4 times 20 gives us 80. Okay, which is 8 longs. And then over here, you've got, again, the 3 units. You're multiplying by 4, and that gives us 12. If we break it down over here in the more standard model, right, we've got 4 times 3 is 12. And then we multiplied 4 times 20 to get the 80. And then scoot over, and then we multiply 10. I'm ignoring the 4, right? 10 times 3 is 30. PowerPoint's blanking out on me. And then 10 times 20 is 200, and then we add all those together to get 322. Got another model for you. Now check out this lattice multiplication algorithm. See what we're doing? We're multiplying 23 times 14. We have 14 written across the top, 23 across the sides. Okay, so you make a big rectangle or square out of this, okay, and you have a box for 2 times 1, a box for 2 times 4, a box for 3 times 1, and a box for 3 times 4. You remember the lattice algorithm that we did before with subtraction, addition? You have 2 times 1 is 2, you have 0, 2. It's actually with addition that we did the lattice algorithm. And 2 times 4 is 8, that's 0, 8. 3 times 1 is 3, that's 0, 3, which really implies 0 tens and 1 3. And 3 times 4, actually, it would be 0 hundreds, right? And 3 tens because you're really multiplying 3 times 10 right here. 3 times 4 is 12, which is 1 10 and 2 units. Now what happens when you have the triangles in here in the lattice, you add down. Notice here we have a 2. Here we have 8 plus 1 is 9 plus 3 is 12. Carry the 1. And then this is your hundreds. 1 plus 0 is 1 plus 2 plus 0 is 3. And then here we have 0. So the answer is 322. Now this is just a personal thing for me. I think that's a cute trick, but I'm not sure it makes me feel better about exactly what's going on. But it is a method to get the job done. If I really want to see what's going on, I feel better about the traditional method here. We have 4 times 3 is 12 when I multiply the units together. Then 4 times 20 is 80. Here we have 10 times 3 is 30, and then 10 times 20 is 200. We add down, we get 322. Now here we have, I know this is your favorite, base 5 multiplication. We have a base 5 multiplication table, and then we're going to try to attempt to do a base 5 multiplication problem. All right, so let's fill in the table. Remember, a table, you're just multiplying 0 times 0. We know that's 0 in base 5. 0 times 1 is 0. 0 times 2 is 0. Why? Because 0 times anything is 0. As a matter of fact, we could go straight down this column the same way. 1 times 0 is 0. 2 times 0 is 0. 3 times 0 is 0. 4 times 0 is 0. Now, let's move on and go across and do our ones. How about 0 times 1 is 1, right? I'm sorry, 1 times 1 is 1. I said that wrong. I did it right, but I said it wrong. 1 times 2 is 2. 1 times 3 is 3. 1 times 4 is 4. 2 times 1 is 2. 2 times 2 is 4. Now, remember, we're base 5, so we don't have any digits larger than 4. So when I multiply 2 times 3 and get 6, that's base 10. But in base 5, that's a 5 and a 1. So 1 5 and 1 1 gives us the number that we visualize is 6 items is 6. Let's try it again. 2 times 4 in base 10 is 8, which is really 1 5 and 3 1s. I'm going to move across here. 3 times 1 is 3. 3 times 2, there we go. The number is 6 in base 10. That equivalent numeral in base 5 is 1 5 and 1 1. 3 times 3 is 9, which is 1 5 and 4 1s. 3 times 4 is 12, which is 2 5s and 2 1s. Keep going. 4 times 1 is 4. 4 times 2 is supposed to be a 4. 4 times 2 is 8, which is 1 5 and 3 1s. 4 times 3 is 12, which is 2 5 and 2 1s. 4 times 4 is 16. Hey, that's 3 5s and 1 1. Now I have that table typed up for you as well. Hopefully we didn't make any silly mistakes. And there's the typed up version. It helps to have that in front of you when you want to multiply. So let's attempt to multiply 21 base 5. Again, I have to stop myself too, right? That's not 21. 21 is a base 10 number. That's 21 base 5 times 3 base 5. How can we handle this? Well, here we go. So look, we write it out. It helps you see this. A column for 5s and a column for 1s. So 2 1 means we have 2 5s and 1 1. Times 3 base 5, which is really 0 5s and 3 1s. You could write that in expanded form. 2 1 is really 2 0 plus 1 times 3 base 5. You could multiply each of those times 3. So 3 times 1, this will be using the distributive property, right? 3 times 1 is 3 1s. 3 times 20, right, is not really what we're doing here. It's 3 times 20. Now remember, 3 times 2, over here on your table, you got 3 times 2, right here is 1, 1, and because of the 0, it's 1, 1, 0, plus 3. Now we know 1, 1, 0 plus 3 is 1, 1, 3 base 5. Now you could handle it a different way. It's the same idea though. So first we multiply 3, make sure my pen is working properly, 3 times 1, that's just the units, and that gives us 3. And then we could multiply 3 times 20. Again, 3 times 2 in base 5, we've got marked over here as 11, okay, or 1, 1. Don't read it 11, it's 1, 1, which means 1, 5 in 1 unit. And then, since it's scooted over, it's times like 20, like we have here, or 2, 0. It'll be 1, 1, 0. And then we can add down and get 1, 1, 3 base 5. Is that not just the most confusing thing ever? Let me know if I need to re-explain that. I've got another one for you here, and then when you try this in the homework, if you struggle with them further, let me know, and we may record some more video on multiplying with different bases. So one step at a time. We've got 1, 0, 1, this time base 2. We could even do a table base 2 if you needed to see that multiplied out. It's not quite like the table before. So we have a 0, 1, and that's it. Okay, and then we have 0, 1, and then we complete our multiplication table, and here we go. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. There's your table right there. So when we go to multiply it out, I'm just going to recopy the problem for the space. Okay, now let's look at our units place. Okay, so we're multiplying 1, 0, 1 times this 1. So again, 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1. Then we move over and we multiply 10, okay, or we could scoot over like you do in the traditional method of multiplying. You scoot over and you have 1 times, right here, this 1 times 1 is 1, 1 times 0 is 0, and 1 times 1 is this 1 right down here. And then you add down base 2. So when you add down, you've got the 1, 1, 1, 1 base 2. So again, don't let yourself read that 1,111. It's not, right? It's 1, 1, 1, 1 base 2. Now, how about some mental mathematics techniques? Again, why do you need to know mental mathematics? It's nice to be able to do some of these calculations in your head for quick calculations, and then that's different than estimating, which is also good to be able to do in your head, and you're getting an answer that's close but not exact. But the mental mathematics is an exact. Front-end multiplying. This is a nice way to do multiplication in your head. You know, when you multiply 78 times 4, you're really using, you can use the distributive property. It's like 70 times 4, and then multiply 8 times 4. And both of those are things that you could do in your head. We know 70 times 4 is 280, because remember, when you multiply by zeros, you just carry over that 0. So I'm really thinking 7 times 4, which is 28, and then I add the 0. And then, of course, 8 times 4 is 32, and in our head we can add 280 plus 32. That front end multiplying is a great way to multiply in your head. There's another method, and it depends on the problem that you're dealing with, but compatible numbers, things that are easy to multiply. If you have to multiply 2 times 8 times 5 times 40 times 5, A way to make that faster is you have 2 times 5. That's a quick one. That gives us 10, right? What else do you see would be easy? How about 40 times 5? Real quick, that's 200. And that still leaves you with an 8, which is not going to be bad. To multiply 10 times 200, which is 2,000 times 8, it gives you that result of 16,000. So recognizing what's easy to calculate can really break your problems down and make it much easier. And then sometimes just thinking in terms of money. When you multiply by 25, it's like quarters, right? So you have 84 times 25. Instead of trying to do that calculation in your head, think about it as 84 quarters. And when I think about quarters, I just divide by 4 to figure out how many dollars. So 84 divided by 4 gives me $21, which is 2,100 cents. Of course, that doesn't work for everything, but multiplying by 25 is a good way to think about that in terms of money because you're thinking about quarters. Now notice this next problem is an estimation problem. Now remember, an estimation problem is when you're rounding, essentially. You're just trying to get close to the answer. You're not concerned if it's off a little bit. So really quick calculations, this is helpful. It's helpful in checking your work, your actual work. You can just look at it real quick and go, yeah, that answer is roughly right. Start multiplying at the front. So 400 times 9. That's that front end multiplying like we did earlier. Again, just change that to 400 times 9. Next, we're going to multiply. We're going to round that 74 to 70 times 9, which is 630. Add the 3,600 plus the 630, and you have a good approximation of... My pen is just not wanting to work because my PowerPoint doesn't want to work, but a good approximation of 4,230. Really, we rounded. It's like we rounded to 470 times 9. That's what that is right there. But that front end multiplying, and in this case, front end estimation is a good way to handle that. Now, that was my last slide, but I ran into a homework problem that you might want a little bit of assistance with. So here we go. Okay, so this problem requests that we find the least values of A and B such that 4,3A is equal to 3,4B. Wow. Okay, so what's going on here is these are different bases and we don't know the bases. So the 4,3 on the left is base A and the 3,4 on the right is base B. And I would like to walk you through a method that I use to get this done. You might have your own way of thinking about it, but it's kind of a challenging problem, so I would like to talk you through it if you're interested in listening. So here we go. It says, explain how to find the least values of A and B. Choose the correct answer below and fill in the answer boxes to complete your choice. So at first you might want to read these answer boxes to see if that gives you any guideline for how to do it. It really didn't for me. I had to just kind of dig in there hard and work on this. So I'm going to start at the top of the page with some calculations. I'm going to write this in extended form, right? So 4,3A really means there are 4 A's plus 3 units. And that's supposed to equal to 3,4B, which is going to be 3 A's, no, I'm sorry, 3 B's. And then plus 4 units. Now my goal is to solve for A or B. So if you'll notice, if we start trying to solve for one of these, let's just solve for A. That means I have to isolate A on one side. First thing I'm going to do is I'm going to remove that 3. So I'm going to subtract 3 from both sides of this equation. Now that's going to give me, I'm scooting to the right at the top of the page. That's going to give me 4A is equal to 3B plus 1 because I subtracted 3 from both sides. Now to solve for A, finally, I'm going to divide both sides of this equation by 4. So I know this relationship, that A is equal to 3B b plus 1 divided by 4. Now this is in base 10, right? Because when I wrote it expanded, this is really base 10. I'm dealing with 4a's plus 3 is equal to 3b's plus 4, and then I solve for a. Now, a is the base for the 4, 3 number. It has to be a whole number. So what I'm starting to imagine, first of all, your base has to be bigger than 1. Okay, so you remember we didn't talk about anything less than base 2. And you can start just checking this out. This, again, needs to be a whole number. So I need that top to add to something that will divide by 4. So if we start doing that, like if we let b is equal to 2, that would be 3 times 2 plus 1 divided by 4. Well, that's 6 plus 1 is 7 divided by 4. That's not going to work. That's not a whole number. So let's b equal to 3. That would give me 3 times 3 plus 1 divided by 4. That's not going to work either, right? Because that's 10 divided by 4. Also not a whole number. Let's try b equals to 4. So that's going to be 3 times 4, which is 12, plus 1 divided by 4. Also not a whole number. I'm just going to keep checking. So let's try b equals 5. So it's going to be 3 times 5 plus 1 divided by 4. Hey, how about that? That would give, and this is a equals, right? So 3 times 5 is 15 plus 1 is 16 divided by 4, which is 4. So in this situation, my a equals 4, and remember we just let b equal 5. Okay, but that would work, except there's one issue. What is the issue? Well, here's the problem, y'all. If I have base 4, then 4, 3 is not an allowed number, right? If you're dealing with base 4, your digits don't go any higher than 3. So now let's look at our answer choices. It says the least values such that a is greater than 1 and b is a whole number are a equals 4 and b equals 5. Since this value is not possible, it's not possible, right? I'm looking at answer choice A. Because there is no digit 4 in this base, the next least values are found, which are possible values for A and B. So this is what's going on right here, because I'm not allowed to have 4. Even though 4 and 5 work for the equation, I'm not allowed to have 4 and 5. So you know what I have to do now? If I select that choice and it's right, and I can't do this because this is not real-time homework, it's a copy and paste situation, but I have to find the next numbers that will make this work. Now remember, we've checked through 4. Okay, I'm going to do a little bit of erasing here and figure out what could the next numbers be that will work. I still have this relationship that a is equal to 3b plus 1 divided by 4. So let's change colors. So now this time let's let b equal 5. That would be a is equal to 3 times 5 plus 1. Oh, we did that already, didn't we? Let's let b equal 6. How about it? 6 over 4. That would be 18 plus 1 is 19 over 4. That's not a whole number. Let's let a equals 3 times 7 plus 1 over 4. That will give me 3 times 7 is 21. Plus 1 more is 22, but 22 is not divisible by 4 in the whole numbers. Okay. So how about 3 times 8 plus 1 divided by 4? That would be 25 divided by 4, not a whole number. Keep going, bottom left. 3 times 9 plus 1 divided by 4. Oh, I think we're there finally. 3 times 9 is 27. 27 plus 1 is 28. Divided by 4 is 7. So what could possibly work is that a is equal to 7 and b is equal to, what do we plug in? 9. Now, does that work for the digits listed above? Yes, because 4, 3, 3, 4, all of those digits are less than your base 7 and your base 9. So if we answered the first one correctly, which I feel certain we did, then it's going to ask you what are the smallest that would work, and in this case it would be 7 and 9, where a is 7 is b is 9. And you could always plug it back in the equation originally to check. So we're arguing that 4, 3 base 7 is equivalent to 3, 4 base 9. And you could check that out. This is saying this is 4 7s plus 3 is the same thing as 3 9s plus 4. And that's 28 plus 3 is 31 on the left. 3 times 9 is 27 plus 4 is 31 on the right. And the 31 that I'm talking about is a base 10 number. Yes, we got it. So star down here would be the answer. We even checked it. It's a deep problem. So I really wanted you to see that. So this is wrapping it up right here at 30 minutes. This finishes section 3-4. If you have any questions, let me know. If you're struggling with some homework questions, send them to me. I'll be glad to make a short video or send you an email to get you through the hump. Have a great day.